the universe stretches out endlessly. When you look at it, everything feels calm, like nothing will ever change, as if it's infinitely stable. But what if there's a hidden crack in this seemingly tranquil universe? What if there's a seed of destruction, one that could overturn everything we know about the universe? It all begins with a tiny particle known as the Higgs boson. In 1964, physicist Peter Higgs wondered why some particles have mass while others have none. To solve this mystery, he proposed a theory known as the Higgs mechanism. According to this theory, an invisible field, called the Higgs field, permeates the entire universe. Particles interacting with the Higgs field experience a kind of drag, like swimming through water. This interaction gives rise to what we perceive as mass. Particles interacting more strongly with the Higgs field become heavier, while those with weaker interactions become lighter. Isn't that incredible? The idea that mass, long believed to be fundamental, is in fact the result of interactions. The clearest evidence for the existence of the Higgs field is the Higgs boson itself. But for decades, the Higgs boson, once dubbed the God particle, remained undetected. That changed in 2012 when scientists finally discovered it. At CERN, the European Organization for Nuclear Research, lies the world's largest particle accelerator, the LHC, Large Hadron Collider. Scientists used it to accelerate protons to nearly the speed of light and smash them together. In doing so, they detected the Higgs boson, long predicted, but never directly observed until then. Naturally, the Higgs boson appears only for a fleeting moment after a collision, then instantly decays into other particles like quarks or leptons. Still, it marked a historic milestone, the first direct confirmation of the Higgs boson's existence. The Higgs field truly exists, and it permeates the entire universe. The Higgs field gives mass to every particle in the universe. It serves as the most fundamental basis for matter existing as we know it, the universe behaving as we know it, and for us, simply existing. But as scientists studied the Higgs field, they noticed something unsettling. The energy state of the Higgs field, permeating all of space, seemed slightly off. Everything in the universe tends to remain in a stable state, or transition into a more stable state. Here, stable state refers to a condition in which potential energy is minimized. For example, a stretched rubber band returns to its original length. A moving object gradually comes to rest. An object held high eventually falls to the ground, because each system tends toward its lowest energy, most stable state. In physics, this most stable state is called the ground state, or simply the vacuum. Yet according to measurements, the Higgs field may not be in a true vacuum, but in a false vacuum, a temporarily stable state that isn't the lowest possible energy level. This graph shows how stable the Higgs field is predicted to be. The red region represents an extremely unstable state, one that could decay easily. In contrast, the green region represents a truly stable state, the ground state, or true vacuum. But our universe doesn't lie in the green region, it's in the yellow region. Yellow represents a metastable state, temporarily stable, but still in a slightly excited state above a deeper, more stable one. Let's imagine a simple potential energy graph. If we place a ball near the edge, what happens? It immediately rolls down into the pit. That's the red region we mentioned earlier, the unstable one. When the ball rolls down, wobbles a bit, and finally comes to rest, that's the green region, the stable one. But the potential energy graph of our universe is a little different. The ball hasn't fallen to the very bottom. It's temporarily stuck in a shallow dip midway down. That means we're in a false vacuum, while a deeper, more stable energy state, a true vacuum, lies somewhere beyond our universe's current state. Scientists suspected there might be a mistake and repeated their measurements over and over again. But the more precise the measurements became, the more confident they grew in the result. It's hard to accept, but all signs point to our universe being in that state. For now, the universe remains stable, held in place by the energy barrier surrounding this false vacuum. But what if some trigger gives the Higgs field enough energy to overcome that barrier? What would happen then? As mentioned earlier, the Higgs field gives mass to every particle in the universe. If that energy state changes, so too would the laws and principles that determine mass. Then, the fundamental properties of particles and matter would shift dramatically, transforming everything into unfamiliar forms of matter and the universe into something entirely new. A completely different world, governed by new and unfamiliar physical laws, would come into being. A vacuum decay beginning at a single point would expand across the universe, forming a vacuum bubble just like bubbles appear in boiling water. It would overwrite the entire universe, expanding at a speed faster than light. Of course, the energy required to escape the false vacuum is unimaginably large. Even substantial energy wouldn't cause the slightest ripple. But the problem is, the Higgs field exists in the quantum realm. In the quantum world, there's a phenomenon called called quantum tunneling, where a field can pass through an energy barrier due to quantum chance, even without enough energy. It doesn't jump over the barrier, just tunnels straight through. Scientists calculate the chance of this happening is extremely, extremely, extremely low. But a low chance doesn't mean it couldn't happen, even right now. That's the unpredictable nature of the quantum world. The decay may have already begun somewhere in the universe, and if we ever do spot that bubble, it will already be too late. The only mercy, if you can call it that, is that we won't feel fear. It would all be gone in an instant before we even feel a thing. A seed of destruction found in the smallest of particles. Perhaps we're nothing more than a brief flicker of luck, glowing within this fragile balance.